years. We are really pleased to welcome you every week from all over the world. So I'm Mary, your moderator today. And as most of you are already familiar with STEM imaging, I will give you just a brief overview of the company and of our academy before starting with our topic. Our topic today, inspection transparent objects. So, Stemmer Imaging has been a leading international supplier of machine vision technology for over 30 years. We are represented by 20 offices in Europe, Latin America, and Asia. We are 430 employees, most of us with a proven technical background, and we achieved a turnover of 109 million euros in the last financial year. One of the company's divisions is European Imaging Academy. It offers practice-oriented training courses on a wide range of vision topics, and all our lecturers are experienced experts from the field. We offer our courses as face-to-face events in our training center in Puchheim, near Munich, or in our other offices, and also at your site. All training courses can, of course, also be held virtually. So if you want to get more technical know-how, have a look at the event calendar on our website, or feel free to get in touch with us. It's now time for me to hand over to my colleague, Lars Vermum, the head of the Academy, who will explain us the inspection of transparent objects during the next 30 minutes. You are welcome to post any questions that may arise using the chat function. We will answer those at the end of the session. Enjoy your webinar. Over to you, Lars.
Thank you. Many thanks for the introduction, dear Mary. And now to the actual webinar topic of the day, inspecting transparent objects. Yeah, that's the question. How do we reliably detect features and defects with machine vision, especially when they are transparent? These are the issues we will get to the bottom of today. Our motivation why we deal with this topic today, transparent materials are often difficult objects to inspect. Just here one example. But with the help of a suitable optical setup, the right lighting method, or appropriate inspection technology, however, it is possible to make transparent objects and structures visible, and we will be able to detect surface defects, material cracks, chipping, and impurities. The only question is which approach is the right one, and we will have a look to a full bunch of methods how we can inspect transparent materials. So transparent, translucent materials are hardly visible in transmitted light, but perhaps you are dealing with a colored transparent object, then this could be maybe the right answer to you. Then a colored backlight could certainly be the game changer. As with bright field applications, additional contrast can also be created with backlight applications. A backlight with a complementary light color will darken our object, and the same light color as the component will brighten the object within the camera image. So now you can recognize this very well by the pictures of the screwdriver you see on the right side. Here, with red backlight, the handle appears transparent, nearly transparent, and you can see the metal shaft that is inserted. If you want to measure how deep this one is inserted, this would be a good solution. And you can also see the golden printing that is also on top of this transparent red handle. With green backlight, the shaft and the handle are no longer separable, this would be a good choice if you want to measure some distances just here across that handle. So again, it's your choice how you like to set up this application. Colored backlight can also be used to illuminate non-colored objects. It may be the case that your objects are not completely transparent. So here too, the image contrast can be improved. In this case, an illumination emitting short or longer wavelengths behave slightly differently. Now let's have a look to that. So blue backlight generates more scattered light on the surface of the component due to its higher frequency. It penetrates the material less well and appears slightly darker in the resulting image. So that's the setup we have did here on the right hand side. So we finally end up here with a contrast close to 104%. The long wave red light penetrates the material a little bit better and appears brighter in the image. And again, here the image, the sample image, you can see our contrast is roughly 96%. So in our example, this increased contrast by about 8%. The higher the contrast, the easier it is possible to inspect semi-transparent objects, thin layers of materials, and that might be the right answer for your application if something is also transparent or semi-transparent. Another way to enhance contrast might be collimated backlight. And the best, it's the same price. So ask our sales expert for collimated backlights. We have a bunch of products that we can offer to you. And this directed transmitted light can also be a good choice to make features visible on transparent objects. In the picture on the left, I have taken here a picture of a transparent component with a conventional diffuse backlight. And as can be expected, the contours, the scratches, the cracks are sometimes difficult to see in the resulting camera image. But with the help of a collimated backlight, such features can be depicted with higher contrast, as you can see here on the right. Here, that is the crack. We see here some molding numbers from the tooling. And we see here also some dust and dirt, and also the outer contours much better. So areas with lower transmission are the result because directed light is sometimes deflected in other directions. And this can be easily seen here if you compare these two images. In addition to the shown backlight applications, other lighting techniques also can be used to illuminate transparent objects. We will now discuss these. So let's have a look to the next. We are talking now about coaxial illumination. So coaxial lighting can also possibly help to illuminate transparent object structures. For this purpose, however, an extra large working distance must be selected in order to use only the directional light component of the lighting. So what's your working distance? There's one answer, 100 millimeters. And that will work. Now have a look to the graphics on the right bottom. The object is illuminated from above. Angle of incident is the angle from the outgoing light ray. And so we get here the flat surface bright because of specular reflection, and oblique phases and scratches reflect the light away and appear dark. And this also works well for chipping and scratches on hard transparent plastics and glass. Now let's have a look to some examples. The pictures I have taken can easily describe this effect. On the left side, a glass surface, and this was coaxially illuminated from top, 100 millimeters. The light is reflected on the surface, appears bright, and here the scratches I did here on the surface and the chips in the material are completely different. They appear dark, as you can see here. And on a second example, I have illuminated a transparent acrylic glass plastic from above. And again, it's nice to see that scratches, even here, fingerprints, and the injection molded logo appear dark, and the surface quite bright. In short, sufficient contrast for the detection of features and defects. So easy to see, easy to inspect. Next, now we talk about dark field and transparent materials. Dark field technologies can also be used for the inspection of transparent objects. So this lightning type generates very flat incident light from all sides. So typically it's also a ring light, and the LEDs are embedded in a very low angle. And due to the large angle of almost 90 degrees to the surface normal, which means absolutely parallel to the surface, there's a specular reflection on the surface. All light is reflected almost completely away and therefore not detected by the camera. The image appears mostly dark, but features as scratches shine brightly because they scatter the light towards the camera. This works well for glass breakouts and scratches on hard transparent plastics. Particles on the surface like dust and dirt or even fingerprints are also clearly visible. And maybe that's what you can also have a look with your smartphone. If they are in the right angle and low angle, maybe you can also inspect then dust and dirt on the surface. And that's the way how it works. Now let's have a look at the pictures I have already illuminated with the coaxial lights. Even with dark fields, we can create contrast in the image to make the features visible. Compared to the coaxial lighting, the image information is inverted. So this surface now is dark and the scratches and the chipping and the outbreaks appear bright. In the picture on the right, same behavior. Scratches, fingerprints, and injection molded logo appear bright. The flat surface of the transparent material appears dark. It is important to say that for such inspections that you have a dark background behind the object. Otherwise, this technique will not work. And I think, same with coaxial illumination. Now let's talk about laser triangulation and transparent objects. In principle, the use of laser triangulation is difficult with transparent media because the laser just penetrates the material almost completely and reflection is not visible to the camera. The reason for this is that with conventional 3D profilers, the laser source is positioned perpendicular to the component surface and the camera is placed at an angle from the side with roughly about 30 degrees. And the solution to this problem is to work with large triangulation angles in specular reflection, where both angles are the same, like shown here in the diagram here on the right top. The solution is possible with individual components, and in this case I would even use a maybe a telecentric LED line projection, or also with special ready-to-use 3D sensors, like especially the LED model, LMI 3D model, the profiler 2512, or the LMI 2522. So these are special models, as you can see here. It's not just the standard way how to project the laser line. So there's a special optical element, and so the light, the laser light, is more emitted not from a point, but from this special optical element with lower opening angles. And this is good if you go on objects that are very shiny or even transparent. Yeah, give it a try. Also, 3D applications are possible on transparent objects, but typically the components have to be flat. So complex 3D structures are not really easy to inspect, even with this technology. What's next? We can also use polarization effects for the inspection of transparent objects. So one possibility is the use of polarizing filters also for backlight applications. This sounds really funny at the first, but we will see how that will work. In this case, a polarization filter foil is attached to the backlight, and additionally, another polarization filter is attached to the lens. So this would be the standard setup. That's what you can see here. That's the normal backlight, and here on top we put the polarization filter, and that's why we have less transmittance here in that area. And in the first step, both filters are placed in a cross position to each other. And this is done by turning one of both filters by 90 degrees. So first we have an unpolarized light source. Then we put the film on the backlight, and then we get linear polarized light. And by turning the filter in front of the lens, we can decide what we want to pass through. So in a second step, the real measurement is done, and optically active materials rotate the plane of oscillation of the polarized light, and therefore they become visible again in the camera image and can be inspected. And also tension lines and optical stress is getting visible, as you can see here on the bottom. Here is one example of how a transparent object was made visible with the help of polarization. So the measurement of stress of this transparent plastic was not examined in detail. It was rather a robotic pick-and-place application that was implemented here. The contrasts in the pictures on the far left are rather low, as you can see here. That's the backlight, that's the transparent material, and we have really not that big contrast. And so it was really difficult to detect. And depending on the rotation of the second polarization filter and the appropriate exposure time, the images look different. So in the image strip on the far right, I think that was the best setup I was possible that I can achieve. And you see the object contours can be seen quite clearly, and everything is easy to detect in the image. So we don't inspect the tension lines, but the outer contour, yeah, that is brilliant to see. And again, we got very, very robust applications here. And another example for you. How does the current structure look like here? So in this case too, there's a polarization filter in front of the backlight and in front of the lens. And the test object is a transparent drinking glass. It was this one. Cheers. And on bottom, there was a transparent adhesive strip. It was a sellotape, or in Germany, we call it a Tesa film, or maybe it's a Scotch 3M film for the rest of the world. And this one was placed at its bottom. And with the help of the previously displayed effect, this film strip can be clearly made visible, as well as you can see in this image sequences I animated there for you. Now go one step further. Working with polarization cameras is extremely convenient. So this could be the professional way to do many things at the same time. So instead of a single polarization filter in front of the lens, there's a micropolarizer on each sensor pixel. With line scan cameras, this is very easy to solve. So on existing quad-line CMOS sensors, entire sensor lines were simply coded with different polarization directions, as you can see here in the diagram. One coded with 0 degrees orientation, one with 90, another with 135, and another one was unfiltered. And so we get the full lines with different orientations. And in this way, the light intensity with different polarization directions can be acquired at the same time at full camera resolution. And this is a brilliant way to do some transparent foil inspection. But also cameras are available with special polarization sensors from Sony. So a very typical one would be the IMX250MZR. That's the thing that is different to the standard 5 megapixel sensor. And there is a corresponding filter mosaic with different polarization directions installed. And this is done by a nanowire grid on the pixels. So one pixel is coated with 0 degrees, another with 45, another with 90, and the last one with 135 degrees. So that's one calculation unit. And like on a Bayer deburring, now we have all that information here in the surrounding pixels, and we can calculate now. Now we measure the intensities, so the grain tones of all sensor pixels, and then the Stokes vectors can be calculated with simple formulas. And from this, and that's the thing that is really interesting, the degree and the angle of polarization can be determined for each pixel. In this way, we can detect defects, scratches, impurities, and this also works even with transparent materials. So if you want to know more, please contact us or come and visit us at the European Imaging Academy. Now, another trick how to make transparent features visible. And now let's talk about deflectometry using a backlight. In most cases, this method is used in incident light to detect surface defects. And this is good for detect slightest angular changes, such as paint bubbles or metal dents. But how does that work with backlighting? So the light is indirectly emitted from a light source that feeds light into a glass plate from the side. As you can see here on the left image, the light is produced here at the side and the LEDs just light into this glass plate. And coating strips are placed on the glass plate for this purpose, and they create a line pattern of light strips. And now the trick. The optical anomalies of the transparent objects cause a distortion of the projected pattern. And this depends on the object geometry and some other optical properties. Let's have a look. Here are some photos of the test sub setup and the results. Here, the object, champagne glass, a real cheap one. And here, the camera, here in between the glass. And at the end, like a standard backlight, we have now here this special one. And that's the resulting image we get now. And due to the local optical anomalies, so we have different layer thickness and curvature, the stripes are distorted. Defective glass, therefore, could be sorted out during production. So that's how it looks like. Here another example. In this case, the glass has no different wall thicknesses, but some air inclusions. So the air bubbles lead to optical effects due to their shape deviation and their different optical density. So it's air, it's not glass. So they have different optical density. And again, the stripe pattern of our illumination is also distorted, and the air bubbles lead to the formation of knots in the image and thus can be easily detected. Here, that's what we don't want to see, but can easily find in the image. And here is a very, very small one. And we were also able to detect anomalies like this. Now, finally, some inspirations for you and some further examples. We have not the time to discuss them all in detail due to time limitations. Maybe it's worth to come to one of our trainings and talk about this. So perhaps your transparent object is a transparent adhesive, so some glue that you want to make visible. And so I would give it a try with UV radiation and see if there is some fluorescence. And then please also use a suitable bandpass filter to clearly highlight it. Yeah, and often we also have to inspect transparent liquids such as water and other organic substances. And they absorb in the infrared at certain wavelengths. So they have a special NIR fingerprint. A special INGAS camera, indium gallium arsenide detector, so an INGAS camera from our product portfolio and a suitable bandpass filter could be maybe your solution. And maybe it's a little bit more complex. Maybe your organic foreign substances and transparent materials are a little bit more diverse and complex, which you have to differentiate. And in this case, maybe hyperspectral imaging could be the right. And there we inspect larger continuous spectral sphere ranges, and all the waste sorting is done with that technology, and we are able to see differences between the materials and sort them. And the final example is the shape from silhouette method. This method generates 3D reconstruction with many, many backlight images from different directions. So you put the part on a turntable and take hundreds of images, and then you can even do a 3D reconstruction of a transparent object. Yeah, these were some examples today from the subject of inspecting transparent objects. Before we start now with questions and answers, some more short information for you. So do you need some own know-how? Stemmer imaging could be a good choice. We offer on-site trainings, and they are all designed as hand-on training. So learning by doing is important for us. We have all the hardware here. And experienced trainer give you practical tips also for your own application. Current topics and dates can be found on our website. For further support in Corona times are our e-learning classes. So we offer there a little bit more compact online training sessions. And we do there a lot of practical live demonstration. And The variety is also guaranteed. Our courses contain also online and offline exercises. And the best, the participation from the home office is also possible, and traveling is not needed. We hold our classes mainly with the help of Microsoft Teams. And of course, we do a lot of individual trainings, so please contact us what's possible there. But this can be easily seen, but not always with the camera you have chosen and the wrong lighting. And we also support you with feasibility studies to find the right components and their right setup for you. If necessary, we also establish contacts with machine integrators if you don't want to make the solution yourself. And yeah, now many thanks for you for your attention. And now questions and answers.
So thank you very much, Lars. Yes, there is a question we often answer. The question is if we share the presentation. And
That's
actually I have to
yeah,
no.
that's easy to answer. The answer is no. I do not share the presentations. They are part of the European Imaging Academy. Feel free to join our trainings. This is a free webinar, and that was all for you. And my recommendation would be if you want to see it again, we will also later on have some offline recordings for you. You can still register then the next month. And also Machine Vision Handbook is also available in German, in English, and in French. You can get some printed hard copies, just order them from our website. And we have also our handbook available, and you will find it on our homepage under the topic Learn. There you will see a link to our handbook of machine vision.